Hello, biologists. You probably remember this slide from last lesson, and probably sounds a lot like probability. That's what we're talking about today. You'll see here, we took a two-trait cross and broke it down into parts. We had one part and two parts, and we did that to make it a lot less crazy, because if I go back a couple, if let me click, here we go. Even two-trait cross was really crazy. You might have caught a little peek of what I'm getting at here, but that was 16 boxes. You'll notice these go up by powers of, like, they're exponential in their growth. So if we were going to do three traits at the same time, it looks like this, and that's crazy. I certainly don't want to do that. I don't think you want to do that. I don't want to have to look through those. No one wants to have to look through those, so there must be a better way. And there is. We're going to use just some basic probability tricks to break down these bigger problems that involve 3, 4, 90. I won't get that high, but mainly three traits. We're going to break them down into a little probability um, way of solving them just using individual Punnett squares. So you may have seen this in your homework, a question a lot like this. It says, consider a trihybrid, so that means three genes this time, all heterozygous. A trihybrid cross between two organisms with these genotypes. Big A small a, big B small b, big D small d, and the same for the other. What is the probability that an offspring from this cross will be a dominant homozygote for all three characteristics? So capital A, capital A, capital B, capital B, capital D, capital D. Dominant heterozygous across the board. Now, based on what you saw in our dihybrid cross, you may have an idea on how to start this, but I'm going to give you a preview. At this point, I'm going to assume that you can do a basic one-trait Punnett square. If not, we have a couple videos on that to go back on, but I won't go over each step here just to keep this concise. But let's say we were going to make a Punnett square for each of the traits individually, and that's what you're going to do to solve these problems. You're going to make three separate Punnett squares, or however many genes you're talking about, and then you're going to take the genotypic ratio from each one of them and just like write it underneath or make note of it. So let's just say we magically did that. So I'm going quick here because this is stuff that we've been practicing a while now. So you should be quite comfortable with these. If not, I do recommend go back to the single trait problem videos. They're still on the bio playlist here on the same channel, and get that solid before coming here. And that's all good if you want to go back to those. But if not, and you're able to get these phenotypic ratios pretty quickly, then you're ready to extend them and do this whole tri-hybrid probability thing. Cool. Awesome. So it's asking us here to find the probability of the offspring being a dominant homozygote. So we're interested in the dominant homozygous traits, because basically the offspring from all these crosses has to get these traits that I keep like pulling up and back, because those are the dominant homozygous traits. If they get any of the other traits, then they won't have dominant zygous characteristics for every single trait. So we're only interested in these three. Now, probability rules say that we can multiply the probability of these independent events. That means we can just say the probability of AABBDD happening is the same as the probability of AA multiplied by the probability of BB, my initials, multiplied by the probability of DD. So that's 1/4, 1/4, 1/4 equals 1/64. Great. So the probability of a homozygous dominant individual is 1.56%. These questions are deceivingly easy. Once you know how to do these single trait Punnett squares, you can just rattle them off really quickly. Then it just breaks down to selecting the right allele and doing some multiplication. Go through that one more time how we got here. We just took each of the individual crosses for each trait, and A, B, and D, figured out the genotypic ratio for each one of them. Then we decided which genotype we were interested in, and as you see up here, we're interested in big A, big A, big B, and big D, big D. So that's what we circled here. Then we just have to multiply those three fractions, and it gives us our overall probability. And the probability in percentage is 1.56%, and I think you'll all agree this is a lot easier than writing out this entire massive chart, where again, we find as this bounces in, I'll let you see that one more time, as this bounces in the top left, only happens once, this homozygous dominant overall thing. AA, BB, DD, all dominant. That only happens once up here, and all these other ones we would have just been drawing out and have to count them. So I think you'll agree that just multiplying it through is a lot nicer. So that is our probability lesson, biologists. If you have any questions or would like further examples or further clarification, please email me at mrbsciencemb@gmail.com and I'm happy to help. Good luck, chemists. Why do I call you chemists? Good luck, biologists, and have a great day.